Let's have a look at this pattern. If we place two consecutive odd numbers 1 and 3 on the numerator and the denominator of this fraction, we get 1 over 3. Similarly, if we place the sum of the first two odd numbers on the numerator and the sum of the next two odd numbers on the denominator, we also get 1 over 3. This pattern is always true. If we place the sum of the first few consecutive odd numbers as numerator and the sum of the next same number of consecutive odd numbers as denominator, the fraction will always be equal to 1 over 3. This beautiful pattern is known as the Galileo pattern, named after the great Italian physicist Galileo Galilei, because he first noticed this pattern while he was researching on freely falling bodies. In this video, we will see three different interpretations of why this pattern works. So without further ado, let's jump into it. The first approach is very straightforward deductive proof. We assume that the sum of the first n consecutive odd numbers is on the numerator and the sum of the next n consecutive odd numbers on the denominator. We can write the nth odd number as 2n minus 1, n plus 1th odd number as 2n plus 1, and 2nth odd number as 4n minus 1. So we can write the fraction like this. If we modify the fraction a little bit, we get this expression. Now, we know that the sum of the first n odd numbers is equal to n square. This is known as the law of odd numbers. In case you don't know about it, here is a visual proof of the identity. So using this law of odd numbers, we can write the numerator and this part of the denominator as n square. Now this other part of the denominator is the sum of n number of 2n. So we can write it as 2n multiplied by n or 2n square. This gives us n square on the numerator and 3n square on the denominator. As n cannot be 0, we cancel out n square, which gives us 1 over 3. Which is what we wanted to show. Now in the second approach, we will try to derive this pattern from Galileo's third law of the falling bodies. Galileo's third law of falling bodies says that if an object is in complete free fall, that means there is no other force working on it except gravity, then the distance it covers is proportional to the square of the time duration. Mathematically, we can write it as h proportional to t square. For those of you who don't know what proportional means, let's say the freely falling object covers h1, h2 and h3 distance in t1, t2 and t3 amount of time respectively. Then the ratios h1 over t1 square, h2 over t2 square and h3 over t3 square are equal to each other. Now let's say on the first second it covers 1 unit distance. Then according to Galileo's law, on the second second it will cover 3 unit distance. Similarly, we can show on the third second it will cover 5 unit distance, on the fourth second it will cover 7 unit distance and so on. So on each second it is covering the next odd number of distance. That means the total distance covered within first half of the time duration represent the numerator of this fraction, and the total distance covered within the second half of the time duration represent the denominator of the fraction. We can evaluate the ratio of distance covered within the first half of the total time and second half of the total time by using Galileo's law. Let's say the falling object covers h unit distance in t unit time and h of half unit distance in half of t unit time. Then according to Galileo's law, we have h of half equal to 1/4 of the total distance h. That means in second half of the total time it covered 3/4 of the total distance. The ratio of distance covered in the first half of the time and second half of the time is equal to 1 over 3. This is how Galileo found this pattern, and this is the reason it is called Galileo's pattern. This derivation shows how profound the connection between physics and mathematics is. Finally, we have a visual proof of this pattern. We can write the odd numbers one below the other in the triangular form in the following way. Even though there are only 5 odd numbers here in this triangle, we are going to assume that there are n odd numbers here. So this last entry represents the nth odd number 2n minus 1. That means the size of this triangle represents the numerator of the fraction. Similarly, the size of this green portion represents the denominator of the fraction, as this entry represents the n plus 1th odd number and the last entry represents the 2nth odd number. Now if we transform this green portion in the following way, we have three identical green triangles exactly similar to the blue one. If we take the ratio of the area of this one blue triangle and these three green triangles, we will have 1/3, which is our desired result. Beautiful, right?